Pessoal, nós temos 2 minutos para iniciar, né?
Oi, professor, só um minuto.
O Brian não chegou, né?
A gente tá aguardando o professor Brian ainda. Ele vai...
Ele não tá, ele vai virtualmente participar, é isso?
Isso, ele vai conectar virtualmente.
Mas eu já o avisei, viu, Jefferson? Bom dia. Eu já o avisei, ele está preparado para conectar. Hein?
E o Rodrigo Pastel está presencial. Professor Rony. So actually, thank you so much for all. You are here in order to fulfill the requirements for the degree of Doctor of Science in the program of Aeronautics and Mechanical Engineering of Materials, Manufacturing, and Automation area. The PhD candidate is Rodrigo Metzger da Silva, having as his advisor Professor Dr. Rodrigo Rego from ITA, and the proposed title for this thesis is Early Failure Detections of Gear Contact Fatigue Through Machine Learning Techniques. The thesis committee composition is led by me, Jefferson de Oliveira Gomes, also from ITA, as a chairperson, and Professor Rony himself as the advisor, Professor Dr. Wesley Oliveira Rodrigues as internal member of ITA, and two external members, Professor Rodrigo Pastel Pontes from Senai, Ceará, and thank you so much, Professor Brian Shaw from the Newcastle University, Professor Dr. Brian Shaw and Professor Dr. Rodrigo Pastel Pontes. So, and then on behalf of Aeronautic Institute of Technology, I would like to thank you, professors, for your very important contribution. This proof is divided in 3 steps. The part 1 is the candidate has 50 minutes to expose the proposed thesis. And part 2, the thesis committee will argue the candidate. That's very important, professors. No time limits for arguments. The audience is allowed also to technically please argue the candidate. Some observation, Professor Shaw, you can do your argument for sure in your mother language, and the other members of the committee feel free to choose your language, and the candidate feel free also to answer as you want. Okay, for sure. Professor Brian Shaw, I would like to thank you if you can answer in English, please. So you can start, Rodrigo, please.
All right. Thank you, Professor Gomes, other members of the committee. I would like to thank you all for your time and availability of being here today to evaluate my research itself. So my research is entitled Early Failure Detection of Gear Contact Fatigue Through Machine Learning Techniques. And this presentation will be divided in 4 sections with the motivation, the materials and methods that were used to develop, and we go through the results and discussion, and by the end we will finish with conclusions and next steps. So the motivation of these works, this research starts with the concept of innovation cycles, where we can see that the waves of the innovation cycles become shorter and shorter alongside with the evolution of the technology itself. And we can say that for industry specifically, is mainly driven by the digital transformation. And with it, we have a high demand of data. So how can we deal with this high demand of data that is becoming with AI, robots era that we are right now? And since we are on this context, the gear market would not be different. So we have tendencies that are somehow linked to monitoring equipment. So monitoring the operation of equipment. So when you look to the tendency of gear market, as we are speaking of high operational times, high rotational speeds, increased reliability, they are all somehow linked to monitoring the operation of these devices of this itself. But why are we talking about gear market specifically? Well, when we look to the costs of gear failure, and we look to we can see that for different industries, it represents an important portion of the equipment operation. So if we look to the cost of manufacturing machines downtime in the UK, for instance, we have up to 2017, up to 180 billion pounds a year of costs in downtime for manufacturing equipment. When you look to the energy sector for wind turbines, you can see that 33% of the time of the downtime of the equipment are related to gear failure specifics. And when we look to the gearbox itself, the 6% of the faults of gearbox are related to gear issues. So in this context, where gear are being highly demanded and data is being generated, we look into the gear failure mode where the identification is done by visual inspection, which means that's the case of gear contact fatigue, sorry. So when we look to gear contact fatigue, we have characteristics of removal of material in the surface. So we have a surface damage mechanism that is occurring on the gear. But when we look to the standard that describes how to identify this failure, we are characterizing as a damaged area. So to do it, so we need a visual inspection. So we use this standard as a reference to a 4% of damage. Of course, that we know that if we have some teeth damage on the gear mesh, this damage will provide vibration, will generate vibration during the mesh itself. However, when we look in the eyes of the standard itself, that we look for the 4% level of damage, we go through a few challenges on this early detection. So it should be easier to identify this failure through vibration when we are talking about high levels of damage. But when we look to the 4% itself, it's not going to be that easy. We have some overlap between the vibration generated by the failure itself and the vibration of the operation of the equipment. So this mixing of challenge on identify the failure is what is driven this research itself. And when we look this characteristic specific on the literature, so we go to the observation that studies of vibration analysis struggles to detect early stage gear contact fatigue, and you look what's causing that on the literature, we can see that we have a lack of studies in early stage. So we can see that for different applications, we have slightly beat, even when you have slightly beating, for instance, for this particularly study, we already have more than 4% of damage being applied in the gear. We also can look on application of different features as inputs. So we don't have a consensus on which feature should be good to early failure detection, and not, and the other side, we have different applications of it. And we also have, for studies that do the simulation that apply the induction of damage to identify the failure, we have a simulation of damage that is way more advanced than the defined by the standard itself. So with that, we came with the question, how can we improve the early damage identification? And when we look to the alternatives on the literature itself, we see that machine learning is an alternative, because we can have from the background that machine learning models can be used to improve pattern recognition and data classification. So when we look on the literature of that for machine learning in vibration to identify different types of failure, specifically for gears, we find a few challenges. First of all, we have different types of failure being applied. So we don't have a specific application of machine learning for gear contact fatigue, for instance, and for different levels of damage also. We have also different frameworks being applied, so we don't have a consensus on which machine learning should be applied or how should be the pre-process techniques for the application of the machine learning. And we also have some general models developing. So most of the studies are doing tryouts on different features to apply on the machine learning itself. So this is one of the things that we find on the literature related to using machine learning vibration to identify the failure. And when you try to combine these three main topics, vibration analysis, gear contact fatigue itself, and machine learning, we come up with a bibliometric review of only 2 studies present surface damage. And the main limitation that we found from these studies is that we have, from overall, a lack of studies in early stage of gear contact fatigue. We also have application of different features as input, so we don't have a consensus on that. And we also have machine learning being applied for different failure classifications and not for one failure specific or different levels of damage considering early stage specific. With that, we define then for this research the hypothesis that the machine learning models can identify incipient stage of gear contact fatigue failure. And this research is driven by the objective of the identification of initial stages of gear contact fatigue failure through machine learning techniques in vibration analysis. And to do so, we divide this approach on 3 research questions. The first one more related to preprocessing and vibration analysis. So how do different preprocess techniques and vibration features respond to evolutionary damage levels? The second one is more related to the development of the machine learning model for the early stage. So which combination of features and machine learning models provide the highest accuracy for detecting damage at early stage? And for the last one, we have how sensitive is the selected machine learning model to different damage levels. So we are evaluating the sensibility of the model regarding different damage levels. So to start the materials and methods, we divide the approach by research question, as we say. So the first one is more related to preprocessing and vibration features. So we need the data to use on the analysis and to perform. So we generate the data from different damage levels on this research question. We also evaluate preprocess techniques and the vibration features. For the second one, we develop the machine learning model using a feature selection technique, and we do then the training and testing of the machine learning model. And by the third research question, we are evaluating the sensitivity of the model regarding these damage levels that we are applying. So we start with the equipment that we use. So here is a big thank you to Newcastle University as a partnership to where we have this back-to-back test rig that we use, where we can control the 3 and 4, we can say, main operational parameters of the test. So we can control speed, torque, temperature, temperature of oil, and flow of oil during the test itself. We use a gear path of face width of 44 millimeters. And although the test rig was capable to control and monitor all of these parameters, we do apply an additional instrumentation on the test rig with 4 accelerometers and 1 pulse sensor. The 4 accelerometers we are applying in 2 main positions, one in the gearbox and the other one at the gear cover, the cover of the gearbox, sorry. And the pulse sensor is used so we can synchronize the rotation of the gear, the gear with the vibrational data itself. So using this equipment, we were able to perform 3 types of tests that we are presenting right now. The first one is the damaged versus undamaged test. So we used a gear that was highly damaged, so we could evaluate the difference between a highly damaged gear and an undamaged one, so we can test different preprocess techniques. We also apply a natural damage testing, which is a standard testing that we use the standard to perform the test and to evaluate the generation of the damage. Here, the damage is developed naturally. And by the last one, to ensure that we have damage at initial stage, we perform a test that was called induction damage testing, where we induce small early levels of damage on the gear itself so we can test it. So going through each one of them, the first one, the damage versus undamaged, we are using a gear, undamaged one as a reference, but which was a gear that didn't have any damage present on the surface, was a new gear to testing in new testing efforts. The other one that was used as highly damaged was a gear with 8 teeth presenting damage above, at least above 10% of area. So it's highly damaged, higher than the standard defined itself. So we test this pair in both wheels, the same wheel for the both tests. And regarding the operational parameters, we did during the testing procedure 2 main parts: a running part where we use that to warm up the test rig, and a testing part with a higher torque where we were actually collecting the data to use for the analysis on later on. So this was the procedure of the damage versus undamaged test. For the natural damage test, we are using what is written on the standard itself, where we go through the setup of the test rig, the contact pattern test, the running phase also is present here, so we can smooth the surface of the gear. And then we go through the durability procedure, which is defined as a cycle run, where we made periodic inspections on the gear to see if we have the damage, so we can access the damage. So at every inspection, if we have the damage present, in the damage, or if we don't have the damage present, if the damage is lower than 4%, we go to another cycle, and if we have it, we were able to stop the test at 1 because since the failure criteria, we already had achieved it. And after that, we go through a failure analysis to evaluate if the damage presented was actually the damage that we were expecting. So as a result of this procedure, we had one test that the failure was first appearing at the 12 million cycles. So we did great amount of inspections between respecting the minimum of the number of cycles that the standard says. And when we first looked into the gear with damage, it was already at 11.15% at the wheel of the gear pair. So we were able to stop the test at that point, but we aim to continue that to evaluate how was the progression of the damage. And we could see at 19.2 or 9.8, million cycles, that we achieved 22.45% of damage at the gear. So we can see different inspections made. And it's important to highlight that during all of this period, all the data was being saved continuously during the entire test. So we have data from 0 to almost 20 million cycles. And at each inspection, we took photos of each gear teeth. And when we get the failures, we get also replicas of the damage. So we could evaluate it, what was the volume of material that was removed during the test itself. As the last test, the induction damage testing, we divided in 2 steps. The first one was a reference because the idea here was to make the damage an evolutionary case. So we can make a progressive case on the same gear to try to simulate the gear operating in real life. So we did first a reference test where we applied the gear in the test rig. We also have the running and the procedure. The operational values of the procedure was the same as that we used before in the other testings, so we could be able to compare. And after we did the reference, we go through the damage induction of 2%, and the testing procedure, the damage induction of 4%, which is the same, where we took off the gear from the test rig, put on the CNC machine, apply the damage. So we are using the CNC so we could have a repeatable way and a reference to apply the damage itself. So we then increase the damage first for 2% and then for 4%, and then we tested it again, and we measured the damage before and after. And to evaluate the damage itself, we were using images. So we took images for all of the teeth, and we applied through a MATLAB software that we were using to evaluate this relationship in percentage of error regarding the flanking contact and regarding the damage specifically. So the replicas evaluation, we did an evaluation through an Alicona focus equipment, which we could evaluate the depth that was applied of 200 microns for the damage development. And we achieved a result that was, that we agreed the literature was a good result, as the difference before and after the damage, you can see the difference on the depth itself was not very higher. And so we could consider that the damage applied before and after the testing, it was still the same, so we didn't progress the damage specifically. So this is how we evaluated the damage that was applied, and how we evaluated all of the other damage regarding that, regarding area also. For the data analysis, we tried 3 different preprocessing. So we evaluate between 3 different preprocessing. The first one is the raw data. So this is the data that came directly from the accelerometers and the pulse sensor. So with that, we were able to apply the TSA, which is the time synchronous average, where we averaged the data from the raw data. So we use packets of 1 second, so we could make an average for each revolution of the gear. So here we can see that we can represent the data from the raw, comparing with on damage 1. We have pretty much the same, but with less discretized. So that this is the main idea of the TSA. In addition to that, we did a residual signal analysis, where we calculated the residual signal from the TSA, which is basically removing the periodic frequencies related to gear meshing. So not on gear meshing, but periodic frequency that have on the gearbox itself. So we remove the shaft frequency, the gear mesh frequency, and the harmonics of the gear mesh frequency. So we would have only the residual signal, which should be only the damage mainly on the analysis. So with the preprocessing, we also apply different vibration analysis features. So we could identify which one has better relation to the failure specifically. So since we got from the literature 6 of them that have some relation to material removal from the surface, so that this is how we select them. And we also put an additional to that a more recent study from 2019 where it's more specific to pitching progression, which is one of the 2 that we found in the literature before, so we could compare them. On the machine learning side, we applied three different models, SVM, KNN, and ANN, to evaluate how they could identify the failure specifically. And however, how should we tune each one of the models since they have different hyperparameters that should be selected? So for that, we apply the concept of grid search with cross-validation, which is basically we select from a pool of parameters one parameter combination, and we divide the data between training testing. We divide the training parts with different folds, and we get data from there randomly. And we use that to train up an intermediate model so we could get the accuracy of that 10 folds. So we did that for one parameter combination, and then we do that for another parameter combination, and we do that until we find the best accuracy result from this intermediate model with higher accuracy, so we could select the best hyperparameters that we would apply after that. We also divide the data regarding the regarding the data between training, test, and validation. So we did a division so we could have data separated and avoiding specifically overfitting, for instance. And for the boosted one, we use the strategy of using one of the tests for testing and the other 2 for training and validation specifically. As a way of evaluation of the models, we apply the accuracy and the F1 score, which were more related to the results of the machine learning model specifically, and all of that is calculated from the confusion matrix. So the confusion matrix is we always expect that the main diagonal be all the values, because it is where the actual classes are predicted with the model. We get the model specifically. But if you have some of them outside that, we have some true positive, we have some false positives, for instance, that could be related to the sensitivity specific of the model and on that specifically level of damage. And by the end, so we could evaluate all of these machine learning models and all of this development regarding the approach by research questions specifically, which right now we're going to go through the results and discussions, starting for the first research question specifically for preprocessing techniques. So for the time domain, we started the preprocessing techniques looking into the multiple high damage. So we use here a comparison of the gear that was fully damaged. So we consider it 100% damage, for instance. And we look then into the time domain with raw TSA, TSA, and RES, and we also look in the frequency domain.
Colleagues, we had a problem with the internet connection. It was now reestablished. Can you hear us?
Yes.
Okay. So Rodrigo will restart from the slide where he was. Okay. And Professor Gomes, are you fine with restarting at the slide? Okay.
Okay. All right. Okay.
Yeah.
So we're going to go through now the first research question, which is mainly regarding the pre-processing technique. So we have a time domain analysis and we have a frequency domain analysis. And the first thing that we highlight from here is that the TSA pre-processing is still representing the signal, because although we are average regarding the one revolution of the signal, we still have the representation of the gear matching frequency, its first, second, third, and fourth harmonic, for instance, here being presented. In the matter of fact of the RAS, we have a reduction on the overall vibration, so we can identify this reduction on the overall vibration, presenting here looking only the comparison between pre-process techniques for the same damage level. So we still have some frequencies being presented on the frequency domain, and we have different frequencies due to the damage presence also. So even though we remove the gear mesh frequency, we have an increase of these additional frequencies related to the damage specifically. And when we compare the damage versus undamaged test specifically, we can see a great reduction or difference on the overall vibration for the time domain of the RAS specifically. And on the when we compare the TSA, we can still see the gear matching frequencies, so they are still highlighted there with the damage being around. And when we look only for the residual ones, which are removing the periodic frequencies, we can see that the RAS can still increase significantly with the faded presence. So this we also have the presence of the sidebands and just removing the periodic components itself. So this highlights that the RAS can represent better the damage than the TSA, for instance, because we are looking to a data more pronounced, more with a higher amplitude than the others. And this also happens that the RAS can reduce the signal. This also happens when you look to the natural damage evolution. So we have this damage first appears at the wheel during the natural damage processing. And this one thing that actually challenges a little bit more the identification, because we have a small increase in appearance at the frequency domain, because we have the damage being appeared on the wheel and not on the pinion itself. So, however, we can still see this frequency being amplified on the residual signal. So it is also there, it's just in a small percentage, small amount, which is the same we can see on the initial damage levels. So when we are comparing 0% damage in blue with 4% damage in orange, we can see a small difference on the signal. However, it's not very clear to differentiate both of them. Since we know the difference between them, we can point it, but it's not straightforward to do this investigation. So even when we look closer, we can see this difference, and we can see the small amplitude increase, but it's not straightforward to define. So even with RAS, which is giving us an amplification of the signal, amplification of or a reduction of other noises, it's not a big difference perceived in the vibration signal. And this becomes a little bit clearer when we look to the preprocess techniques, to the vibrational features, where we do a preprocessing evaluation through feature extraction. So we bring here two features as example, as the RMS and the energy ratio, and we compare, we can see a small tendency increase with the damage level for energy ratio, for instance. However, when we look for the RMS, it is not. It is always very confusing between them and between the damage levels. And when we apply the RAS, we can see that we have more a standard pattern. We can see kind of a pattern, kind of a tendency. However, it is not straight differentiate. It's not easy to differentiate all of them because they're still a little bit mixed. So the reciprocity increased distinction of favor for some features. However, it is not clearly separable. Specifically, if we go through statistics also. So as a summary for the first research question, if you look into the multiple high damage test that we were comparing the damage versus damage, we can see a severe degradation visible in time and frequency domain. So only using raw would be sufficient to identify the failure because we have a highly damaged gear being tested. The TSA and RAS can enhance clarity, but we already have very clean raw. When you look to the single high damage, it's less evidence, mainly because the damage was present at the wheel. But we still can see some increase in the amplitude. We still can see some frequencies present there. And for induction, the induced damage, we can see a challenge between differentiating 2 and 4, which was actually expected because they are small levels of damage, so it's difficult to challenge the difference between them. However, the rest can isolate the non-periodic components and then can improve separability. And 2% remains difficult. So with that, we can conclude that the rest consistently enhances false-related characteristics, proving most effective for highlighting regular damage contributions. And with that, in the evaluation of the features itself, we can then go to the machine learning development specific for early stage. And we highlighted here the difficulty that is not straightforward to separate that. Especially if you have a continuous test. We're not always going to have the data labeled from the 0%. So we will not be able to classify them with only the overall value of the vibration. So we bring here an alternative to look into the data, so all the features, all the 7 features that we selected, look into them to a pair plot, and we can see a few things. So we have here 7 features that are being evaluated. We can see that some places we have the 4% of damage in orange being clustered, so it has a little bit more differentiation from the others. And however, we still can see some strong relationship between RMS integration and FM4 and M6A, which was actually expected because they are very similar in the equation and how they are actually formulated. And this makes more evidence when you look to the correlation matrix of the 7 features, where we have some strong correlations above 90%. And to make a way of separate them, we apply a technique of feature selection that is called recursive feature elimination, RFE, where we evaluate small potential sets of features. So evaluated first, we evaluated the RFE for only 1 feature, then the block of 2 features, 3 features, 4 features, until we have all of the 7, and it will ranking which one is the best for the specific application that we are using. So with that, we can conclude that some features consistently rank higher, showing greater relevance, and this is because we are evaluated which one is the best around all of them. So a lower value, we can see that from some points, some of them starts to get consistent on first place, and that's why they got the number of 4. However, other features are always ranked lower, considering all of this application. So this is especially when we have smaller subsets. But when we use all of them, we can say this is equal. So with that, we came up with selecting 4 features from that. And it's good to correlate them regarding the application on the vibrational signal itself. So pertussis has a characteristic of impulsive behavior and detection. The energy rate and FM4 are more related to the energy-related measurements that are present on the vibrational signal there from the damage specifically. And correlation coefficient has a signal similarity regarding comparison between undamaged and damaged itself. So using these 4 features that we selected, using all the methodology from the vibrational analysis, we developed 84 models of testing the machine learning model. So we go through different combinations of sensors. So since we had 4 sensors, we could combine them, and we could also use data from only one of them to evaluate it if it would be simpler, it would be better. But we also combine all of the four as an alternative. We use only one pre-processing because we evaluate it as the best one from the first research question. The set of inputs, although we select four, we also put all the seven so we could compare them to see if it was actually a good selection that we did and how was the difference between that using them. And for the other algorithm, we tested three of them that we selected before. So looking to the results of these 84 models that were developed, we have here them divided by machine learning model. So we can highlight a few things from all of these models that were developed. The first thing is that the sensor AI presented a high accuracy alone for different models, which is actually a surprise and a good thing, that since we are using only one sensor to be able to identify the failure cell. We can see that for some reason AX alone decreased the accuracy of the models. We're going to discuss about that a little bit later. And which is also a characteristic that happens for all the three models that we are using. And one thing that is common from the literature is using two sensors that we call here AI and AX. So we have this as both of them in radial position. So they present good accuracy. So the literature saying that's more common is actually here being represented well. But we also can say that more features do not actually mean higher accuracy, because we can see for some cases that using more features was actually decreasing the model accuracy. And when we compare the 4 features with the 7 features, we can see that the 4 features actually perform very similar. So they were increasing the performance of the model, but they were not decreasing that much. So it is comparable since all the models' accuracy here were getting higher than 80% accuracy. So we can say that the developed models were able to identify, all of them actually were able to identify the early stage with accuracy higher than 80%. So with all of this development, we tried to summarize it in a framework so we could then apply that after on other applications considering the early stage. So we started with the data acquisition using the accelerometer and the pulse sensor. The feature extraction, for the signal processing, feature extraction, feature selection, we define the residual signal as the main pre-process technique. 2 combinations, AI, UI, AX, and the 4 features were actually providing good results. When you go to the model development, we see that SVM and ANN, with the combination of word search and cross-validation, were presenting a very high accuracy, so they were considered validated here for the applications. And for machine learning diagnosis, we evaluated considering the different damage levels, percentage, and accuracy and F1 score were showing that 0% and 4% was very good, and for 2% we are getting a little bit challenging on separating them regarding 0, regarding 2 and 4 specifically. So this enables us to go to the third research question regarding the sensitivity of the machine learning model looking through damage level. So again, we're going to use the same data that we had before, but right now, to evaluate the model, we are considering all of the 5 damage levels. So looking to the pair plot specifically for all the 5 damage, you can see some of them clustered, some of them separated. But when we look to the correlation matrix itself, so we don't have actually no high correlation between features. So which is a good thing. So none of the features are being redundant, using a redundancy, which is a good thing that we expected using in applying. So now developing the model using the framework that we developed before, for the 5 levels of damage, we came up with the final evaluation of the model. So we have new models here applying that framework with specific conditions of each one of the sensors that are being applied and the 3 models that are applied here. So we highlight mainly that we got accuracies above 6% for all of them. However, we have 8 models with accuracy above 95%, which is a good thing. And the main thing is that they are for specific conditions. So when we look the AY, sorry, this consistently delivers the highest accuracy, and AX is still reducing the performance. We believe that it's mainly because of the geometric characteristics of the gearbox, specifically where vertical sensors are presenting better results than horizontal sensors, since AX is on the horizontal plane. Both of them are radial to the gear. However, one of them is horizontal, the other one is vertical. And as the best configuration, we selected here the AYC, so a combination of the two sensors on the vertical positions where they were reaching almost 99%. So SVM, ANN, and KNN, both of the three presenting 98 to 99% of accuracy on the testing specifically. And when we look to the final model evaluation, considering now the correlation matrix of it, we can see for most of the damage, they are presenting a good accuracy in identify, which was actually the goal of here. But when you look at scientific specific, for some reasons, we have a small misclassification occurring primarily between 0 and 11, which we can attribute that to the weaker vibration response of the wheel. So since the damage is presented on the wheel, and we were expecting the damage to present on the pinion, but this is something that can happen on natural tests. Although here it's getting a little bit wrong on identifying that 11% on the wheel that is happening. So a good thing is that we have no confusion between 2 and 4, which is a reliable identification of the 4% defined by the standard. So this is a good thing for the models that were provided using this final evaluation. And also, the confusion that we got was between 0 and 2%, which also evidences an SVM. And as an alternative to, let's look into the data that we don't have labeled. What we did was we get the data from the natural damage testing, where we have the period of when the failure appears, which means that before this, we had stopped the test rig, we made inspection, and we did not see any damage. And after that, after we ran, when we stopped it again, we see the damage of 11% on the wheel specifically. And here we are putting one of the models to classify the data to see which class, which results they are giving to us. And you can see here that they are specifically they're specifically predicting the damage as 0 or 11%, which is a good thing, because at the end we had it was 11% of damage presented. So when we look, we have a certain point where we have an increase in the 11% class prediction. And more than that, it's not only the increase. You can see that after that, the 11% class prediction becomes stable. So it continues to predict the 11% until the end of the test specifically. We do not have any prediction of 2 and 4% for the model here, which means that probably the damage increased from 0 to 11 directly. So the material removal was removed directly from 0 to 11, which the model here was able to identify. An additional observation we can look into this is, since we are able to identify this damage happening on site, on the test specifically, if we had stopped the test where the prediction was higher than 80%, for instance, and we consider that for an evaluation, and we had stopped the test right there, we would have reduced by 80% the testing time, which is a good thing. So because we don't need to make periodic stops to see if I have the failure. If I use the machine learning model, if I use this developed model, we can reduce up to 80% of the testing time, considering that we can run the test rig overnight. So we don't have to stop for periodic stop. We don't have to wait for the test rig to code, for instance. And this is a good result that we can bring here for the results itself of this research. And so we can finish the conclusion and the next steps of this work. We divide them by research questions. So the first one is that the pre-process technique was actually improving the signal clarity. So we were able to identify different damage levels. And we highlight here the RAS as the best, or from our scope, the better one for fault usability. For the second research question, the models were actually getting 80% of accuracy for both of them, and some of them getting up to 99, which is a good thing. You can see that AY and AYC was best combinations on the vertical position, but they're not on one. The best result they got from here was the framework itself, where we can make a decision, make a selection of parameters to identify the failure at early stages. And by the end of the third research question, we can see that we were able to match the 4% of damage identification we got a good sensitivity for the 4% of damage. We were missing the 2% specifically. The damage at the wheel remains a challenging because this is something that can happen. It's not actually expected, but it's something that can happen in tests. And for the framework, we couldn't have a reduction of 80% of testing time if you apply models instead of doing what is defined on standard as periodic inspection specifically. So as an outlook for this work, we still have this to resolve this boundary between 2 and 4% damage. So maybe increasing the resolution of damage between that area, we could increase the classification of it. That's an alternative. We still need to improve the detection of the wheel side initiation. As I said, this is not something that we would expect, but it's something that happens. It can happen in the natural tests. So maybe additional tests for that would improve the data set in overall, getting more data to increase the accuracy. We need an alternative also to improve generality of the model is to validate across other rigs and geometry, so we can apply the framework for the other test rigs and other geometries of specifically. And by the end, we have additional testing of machine learning model families. This would be easier to do since we already have the data collected for this test. So we could, for instance, improve the generalization on that side. So this is my presentation. I would like to acknowledge some institutions, some people here for the help of the development of the research itself. So ITA and CCM, colleagues from here group specifically, from CCM also. My colleagues from Newcastle University, from the design unit, which were very helpful always with me and with the test that we performed over there. INDORP, CNPq, and CAPS for all the financial support, and really for all the network and presentations and discussions that we had along this time. I thank you all for your time, for your exposure, and I'm here able to answer some questions if you should. Thank you.
All right. Thank you so much, Rodrigo. You presented in exactly 50 minutes. Very good. Thank you so much. Professor